to go on. And I'm sure that there's much more that could be said about this. But Bob, you have another talk.
There is, because I did a lot of study, and yeah, a lot of these techniques come from the exoplanet work where you had a bright star and you're looking for millimags of drop, and that's where most of these studies come from. The question is, can it be adapted for use for us? And the answer is maybe or maybe not. Okay, so I'm going to say that this talk is more of an announcement than a presentation of a paper, and I'm going to go through it really quickly. There's no reason to spend a whole lot of time on it. The title uses the term calibrated. It's a bit of an odd term, but what it means to me is that the underlying noiseless light curve is known, as well as all of the noise contributions. I just couldn't think of a better way to imply this fact. Okay. Let me get my laser pointer working. So I had seen there were a couple of expressions on the group's IO when people were talking about light curve extraction techniques like optimal extraction. The question is, how do we know what's best? I mean, how do we test these things? We don't know. And so when I started working in this area for PyMovie, I needed such a suite. And so I built it, and it's publicly available now. And I'm just going to go quickly through what's in that. And this is where you can get the public share. It's pretty easy. You just type this in and you'll find it pretty quickly. So each video is a sequence of FITS images. FITS is a really common, everyone's going to be able to read that. And these are the factors that went into making the simulation look like, as close as I could, common occultation recordings. So you can specify the sky in magnitude per square arc seconds. I use typically 17 or 18 or 19, which is sort of, typical for some reason. The seeing, image jitter, which is caused by low altitude turbulence. That's what causes your stars to kind of move around. Image speckling, we saw a little movie of that. We don't see that very much in the videos that we take, in part because we're undersampling. We don't have much of a chance to see image speckling. I take into account the telescope diameter, its effective focal length, its obscuration area. Finally, on the camera, the pixel size, the pixel count, the read noise, the dark noise, the full well depth, the quantum efficiency, the absolute photon sensitivity and exposure time. You can tell I spent too much time doing bench testing of cameras, which, by the way, I'm beginning to think is sort of a waste of time. Scintillation noise is another thing that I take into account. So there's a sight factor. This is actually a multiplier. I'll get into that a little bit more. Your zenith angle, the observation altitude, how high you are. And I simply use the Young's scintillation approximation, which was described in this article. Now, the modification that he did in this paper was to look at the best observatories in the world and compare them with what the scintillation noise actually is, since they can now measure that pretty well. And he discovered that Young's was under approximating. And so he stuck in a factor. And for those best observatories, that factor was some number between 1.2 to 1.5. In these simulations, I used a factor of 4. So I assume that we're nowhere near having the seeing conditions of the best observatories in the world. Now, as a result, scintillation noise tends to dominate. It's typically about 4 times the contribution to all of the other parts. So this is what a single frame would look like. It has 4 images. This is the perfect PSF. There's no noise. It's on a completely black sky. The background is 0. And so if you put a circular mask that's big enough, you will include all photons, and you will have a number that has no noise in it, and it will follow the underlying light curve exactly. This is simply a tracking star. It's on a zero background. It's meant so that if you're using, well, any of the extraction programs, Tangram, iMovie, PyMovie, have no difficulty using this to track on, because as this set of frames progresses, this whole thing slides slowly down diagonally to be able to test the tracking ability of the software. Now, this image is this one, but superimposed on background noise, which is mostly sky noise, but it's got any of your camera contribution as well. It's got shot noise. It's got your read noise. And finally, on this one, I've done something to kind of simulate the speckling that you get, which is kind of a tearing of the images. What's true is that all the pixels here are the same as the pixels that are here. They're just sort of redistributed a bit, as high altitude turbulence would do. And this is usually the target star for most of the tests that I was running. One other thing that is not visually apparent, the background of these two star images is exactly the same. You know, there's a 51 by 51 box that encloses these, an aperture, to use my terminology, and the pixels from here are duplicated in the pixels here, and that's to give that is to take that out of the equation if the background calculation is something that's giving you any trouble. So I typically sample these things with a 41 by 41 aperture, and that means that each of these images will have the same background to contend with. This is kind of a zoomed in picture, and I think that this is a little movie, so I'll just show what it would look like so you can see this thing kind of morphing, changing shape. You can't really see the diagonal motion that's happening. Well, you might notice it a little bit if we go long enough, but you're seeing the jitter. You see this one's moving around. That's your low altitude turbulence. Tip and tilt, they call it in the turbulence literature. These are not jittering in the same way, so they're not in lockstep. They're going in different directions at different times. So that's what that looks like. This is also a movie. It's not going to be particularly boring. It's boring because it's tracking star. It's being tracked, and so really nothing appears to move. So here is the movie of the noiseless one. It looks like the PSF is changing. It is actually, because the center of the PSF is being moved in fractional pixels, and that causes the PSF to be sampled a little differently. And so it looks a little different when you do your digital sampling. But it is true that the sum of the pixels, no matter how it's been changed by where the center is a constant number. And this is what your normal target looks like. By normal, I mean it's not been speckled. It's just being affected by your background noise plus the jitter. And finally, this is what the movie looks like for the target that is being speckled. Each of the FITS files has a meta part, which gives you all of the parameters of the video that you're looking at. So it shows I was using a 3 arc-second seeing, and I decided that there was a little distortion somehow in your optics, so I stretched it a bit in one direction and the other. I get some scintillation, jitter. This is how I do my speckling. I do near neighbor exchanges, and here I just did 2 of them. I set the sky, the target magnitude. Well, you can read it. Anyway, they're all here, and it shows you what your noise was. The telescope here is it was a 12-inch. I took most of these specs from, I think it's Tony's, actually. He's got a focal reducer on it and gives him this effective focal length. And for the camera that I was using with the pixel size of 4.5 microns and his optics, he has a pixel field of view of 0.9 arc seconds. That's a pretty nice fit to seeing of like 3 arc seconds. So that's actually pretty good. Now, here, I'm just going to step through the available test curves. The first one is, I call it a step level, and I use it to measure the absolute accuracy. There are 1,000 points on each step, so you can get good statistics. You know, how well did it measure the intensity at this level versus this level versus this level, and I go all the way down to basically a 5%. So it's a pretty big mag drop. This is an artificial one. It's useful to see if there's any oddities at all in the extraction software that will cause some otherwise hard to see nonlinearity in what it's doing. This is a bright star, but kind of a small mag drop. That's only 0.05 mag drop, but it's actually big enough that with this length duration, the DNR timing should be pretty reliable. It should be within a frame time or two. This one challenges it a bit more. So that means if there's anything wrong with your extraction that isn't really apparent, but then you put that through Piode or AOTA or Live Movie, and you ask where the edges are, you can start to see, oh, well, something happened there. This is would test the ability to have a bright star that goes through almost a complete blackout. This was a pretty big mag drop, 3.275, I think it was. I only printed 2 digits. And then there's a test where it goes all the way to 0 to test whether there are any problems with that. I will say that if you're not careful with Nailer, it will blow up when it drops to 0. Roger will say, yeah, I told you so. I've got 2 real life examples, and these would be difficult to have any real metrics of how it's doing, but it gives you an idea of how the extraction works on a real life. And then there's this real life. This is a nice high row diffraction that's really fun to put through PyMovie and then through Piode and have Piode fit a diffraction curve to it. And all you have to tell Piode is it was a 2.185 mag drop, and you give it the duration and how far away it was, and it fits very well to that. So just a quick conclusion. You want a copy of it, you go here on the occultations.org site, and down near the bottom of that page, you click on this, and that will take you to, I think now it's a Google, what do they call it? Anyway, it's where Google will store these images for you.
Google Drive.
Google Drive, and that's it. I'm going to stop my share and over to Kai, unless there are questions about this.
Tony has his hand up.
Oh, he does? Oh no, he's applauding. Oh, I'm sorry.
Okay.
I
Kai,
didn't know
are you ready to go?